So we've been working on electrical power. We've talked about it with DC circuits. Now we'll be going into AC circuits. And one of the things that's been established, well, throughout everything, power is equal to voltage times current, even as functions of time, the instantaneous power. So when we do this, and these are cosine waves, we end up with some interesting results. What we get if V of t is equal to some magnitude cosine omega t plus a phase angle, and current then is equal to a magnitude of Im cosine omega t plus the I, right? A phase angle for voltage, a phase angle for current. And when we do this, we find that the power function, a variety of multiplications and trig identities, we find we can write it as Vm Im over 2 cosine of plus Vm Im over 2 cosine 2 omega t plus Vv minus Vi. Now, the one thing, we have this number here, or term here, which represents the constant power. There is power being delivered. However, this one, you'll note, it has a 2 omega t here. It is fluctuating. It's not only fluctuating, depending upon the magnitude and character of these things, it could go negative. The resultant could be negative, which means power is not flowing out, it's flowing back to you, or energy is flowing back to you. Okay, this is a bit of a problem. So what we're going to do is actually create a set of voltages that interact properly with one another. First thing we'll do is represent it as phasors. Now, we've done phasors in prior work. What we're going to do now is try to characterize them as in a way that they interact properly. The primary one, our main one, is going to be right here. Now note, if we've talked about phasors before, this is representing a location at time 0. And if we had that, we had this being V1, one of our voltages, we'll want to create another voltage that's out here, V2, which has 120 degrees out of phase. Now, as I do the video, or the animation here in a moment, that will make more sense. Finally, there's another one right here. So this one is V3, and it's at minus 120 degrees. Always remember, this phasor diagram is kind of frozen in time at time 0. And then, the other important thing is if we take voltage divided by an impedance representing the circuit we're driving, we can get then the current for that. With that in mind, with this diagram, and maybe we can make a little more sense of it by going through this animation that will come up next. Now, we had our phasor diagram earlier. Here's another version of that, only plotted by computer. The blue line here is our first voltage. The light blue line down here is our CN, is our current. Each voltage, this is the voltage 2, this is voltage 3, and their corresponding currents. Okay, we're going to take these and put them in motion, which is really what this is representing. This is representing them frozen at time 0, and we're going to move forward now. Right? So once I click on this and start the animation, it's going to start rotating. And that represents what actually goes on with the phaser and what it's representing. It's representing that sine wave or cosine wave down here. And what we will note is that each point we take the voltage times the current that we calculate, and we plot that down here. And what we'll find is that, sure enough, much as we were describing before, there's a slightly negative part down here. It goes slightly negative on one of the phases. Note the other phase is coming in now. It will go slightly negative here, which indicates power flowing back or energy flowing back to us. Okay, so this keeps going and going, and at this point we will come back when it's done. So now that it's complete, and we can see it here, one of the things to note, again, powers are fluctuating. They're fluctuating twice as fast as the voltages. That was the 2 omega t that we saw. And they go slightly negative on each of the phases. However, if you simply add those three up, those numbers at one of these points, add the 3 powers from the different phases, what you find, they are constant. They're going across here, they are constant. And what you end up with is a constant flow of power. That's why 3-phase electrical systems, or power, is so important to us. If you ever see a cross-country transmission line now, you'll look at it and go, yeah, there are 3 lines on that. There are nearly always 3 lines. Now, if you get into a city where you're servicing homes, they split a pair of those off, or one line. But across country, there are always 3 lines, and that's because they want a constant flow of power through that system. That is the whole point of 3-phase. It'll be used in lots of applications and is pretty important.